Observe a butterfly as it opens its wings. The patterns on the left are a mathematically perfect mirror image of those on the right. This balance is what we call symmetry. In geometry, it is a tool used to define exact proportions and structural stability within a shape. For your upcoming exams, you must be able to identify and calculate 3 specific types of this balance: reflection, rotational, and point symmetry. Mastering these concepts allows you to take abstract, irregular shapes and break them down into predictable, testable formulas. Reflection symmetry occurs when a straight line divides a figure into 2 identical halves. If you were to fold the shape along this line, both sides would overlap perfectly. Let's apply this to a regular octagon. How many lines of symmetry can we identify here? First, we draw lines connecting the opposite corners, or vertices. In a regular octagon, this gives us our first 4 lines of symmetry. Next, drawing lines through the midpoints of the opposite sides adds another 4. With 8 total lines, we see a pattern. For any regular polygon, the lines of symmetry equal its number of sides. Note this rule only applies to regular polygons. A standard rectangle, for example, has only 2 lines of symmetry, 1 horizontal, 1 vertical, rather than 4. Mapping these folds proves that visual balance is a property we can measure and count mathematically. Symmetry can also be found by spinning a shape around a fixed center. If a figure looks identical to its original position after a turn of less than 360 degrees, it has rotational symmetry. We calculate this using a specific formula. The order of symmetry equals 360 degrees divided by the smallest angle of rotation. Let's find the angle and order for an equilateral triangle. As we rotate the triangle a full 360 degrees, it matches its original outline 3 times. This means it has an order of 3. To find the angle, we divide 360 by our order of 3, giving us a minimum rotation angle of 120 degrees. On your exam, always remember to state both the order and the angle to provide a complete description of the symmetry. This proves that even dynamic movement around a fixed point follows strict geometric constraints. A more specific case is point symmetry. This occurs when a shape looks exactly the same after a rotation of 180 degrees around its center. Because it takes 2 of these half-turns to complete a full circle, point symmetry is simply another name for rotational symmetry of order 2. Consider this slanted parallelogram. We need to check if it possesses any of the symmetries we've discussed. If we try to fold it, the corners do not match up. This means the shape has no reflection symmetry. However, if we rotate the parallelogram exactly 180 degrees, it returns to its original appearance. It has point symmetry. For a quick mental shortcut, always associate the term point symmetry with the number 2. Identifying these mathematical properties reveals a hidden, perfect geometric balance in real-world shapes that might appear entirely irregular to us at first glance. You now have 3 primary methods to classify balance: folding for reflection, spinning for rotational, and rotating halfway for point symmetry. You have the formulas and the visual logic needed to solve even the most complex symmetry problems. Now, pause the video and use these tools to complete the remaining exercises on your worksheet. These symmetrical laws provide a consistent mathematical framework for verifying the balance found in both geometric figures and the natural world.